So what we're doing today is starting chapter 1, because I believe I did talk about Google Classroom yesterday, stuff we find on this here. So if you're trying to find the YouTube channel, YouTube, that link right there will get you right there. Syllabus is put in there, and then the PDF of the book, because we don't have access to the online version of Big Ideas anymore, because we adopted new textbooks last year, and since Big Ideas, we pretty much told them we're not going to pay for the subscription anymore, they kicked us out of the account. So, I mean, that's how it works. You don't pay for the account, you don't get access to it. So, but we do still have the PDF copies of the Algebra 2 book. So all this here, you can click on it, pull it up. There is a link I will include, because I did find that they do have a digital version of the book online. So this here, I will include this link into your Google Classroom. So we pull it up and just say Oklahoma. Go. So we're the Algebra 2 book, and you have access to the whole book. This is also, just as a side note, I find it interesting. If you notice that when you put all three of the books together, I believe the top one is the Tulsa skyline, and the bottom is Oklahoma City. It is the actual skyline of the city, because all three books actually all fit together to make a picture. I think it's kind of cool they went through the effort to actually put that together, but that's it for the most part. I did talk about the trivia for each week. Yes. All you got to do is answer it. I did put the pieces of paper out, so by the tissue box or little partial sheets, all you got to do is put your name on it and answer it. This week's kind of easy. But something fun you did over the summer break. Yeah, so you want to hand him one, because it looks like, yep, so you can turn that in at the end of the class. You can do those throughout the week. I normally, especially by this point on Monday, if I have not put a new one up, remind me, because there's a good bit that I get going and I forget to do some of the stuff like that, update that. The same is true with my calendar. 9 out of 10 times it's going to be off if I'm trying to keep track of it. Yep, because today is not the 12th. Now, chapter 1 is what we're starting with. Now, chapter 1 is a little bit of everything, because we're going to start off with set builders and interval notation. We're going to talk about systems of equations. We're going to talk about matrices. We're going to talk about transformations, and it will be a little bit of everything. Now, what we're talking about is starting off with is intervals and set notation. Now, it'd be helpful to define what a set is. Now, a set is a collection of objects. And we normally use braces to list a set's members. So if we're looking at this first example, 1, 2, 3, we would use a brace, 1, 2, 3, brace. That's it. We use 2 braces, we list all the members of the set, because the members of this set are 1, 2, and 3. And we get this here. The other example that we have is positive even numbers. Well, the smallest positive even number is 0. And then we have 2, 4, 6, 8, 10. Now, realistically, there's no way for us to list every possible positive even number because there's way too many of them. There's an infinite number of positive even numbers. So once we get a pattern set, when we're listing the set's members, we can use the ... to say and signify that this pattern continues on indefinitely. And that's it for those two. Questions on listing sets so far? Now, one of the nice things with sets is that we can actually call them by their names. Because groups of numbers do have names, we have grouped them together. And the first one that we have is the natural numbers. Natural numbers are naturally the numbers you count on your hands and your feet. And I would love to say I came up with that rhyme, but I definitely did not. So we have that there. Now the boxes in that bottom, we're just going to be filling them in one at a time. All right. So we have those there, natural numbers 1, 2, 3. Now, I will say this again and again throughout the year. Mathematicians are a little bit notorious for being lazy, and not in a bad way, but if we can write something simpler, if we can do something easier, smaller, we don't have to do extra work, we're definitely going to do that. And one of them is natural numbers. Natural numbers are represented by this n with 2 lines. Yep. Yeah, so it's just those boxes right there. So so we're just filling in that one right there. And we will fill it in page by page because we're right there in the center. Because each one's going to expand on the other. Now, what we're really doing, and you don't have to draw this in, is we're looking really at a number line. And the natural numbers, our counting numbers, have given us these here, these 1, 2, 3, 4 going out. Bless you. And we represent it by this n with 2 lines. And it's helpful, especially in proofs when we're talking about mathematics, when we're defining a set. We can use this instead of having to write natural numbers each time. That n with 2 line represents natural numbers. Now, natural numbers are a part of the whole numbers. And the only real difference between natural numbers and whole numbers is that whole numbers adds what? 0. That's it. Natural numbers add 0. So on our number line, the whole numbers is just adding 0. Now, for the most part, there's not really a symbol for the whole numbers. In mathematics, across the board, we don't normally talk about the whole numbers. We just mention it, reference it. Whole numbers does add 0. If we're talking about 0 and positive, it is the whole numbers. And part of the reason we don't talk about it much is because, well, if we're going to talk about 0 and positive numbers, we're just going to say the positive or the non-zero integers. We talk about the integers over just the whole numbers. Or non-negative integers, because integers adds positive and negative numbers. Now the natural numbers was our n with 2 lines. Whole numbers, we decided to do w with 2 lines, even though it really doesn't have a symbol. Anybody have a guess at what the integer symbol is? It's not an I. It's actually a Z. And we'll get to it here in a minute, and it's mainly because the I at this point had been taken up. It's already used it for another set of numbers. So we can't use it for integers. So integers adds our negatives. And as you see here, we're slowly, with each group, we're adding more and more to the number line. Now, the next thing we need to add, or the next thing we're missing, is really the numbers between our numbers here, which are going to be our rational numbers, our fractional numbers, any number that can be written as a ratio of two numbers is our rational number. So now we're starting adding numbers between 0 and 1, 1 and 2, between these points. Any number that can be written as a fraction is a rational number. And like most things in mathematics, we like naming it exactly what it is. Rational, ratio. Ratio is a comparison of two things, two numbers. Rational numbers, ratio, it's in the name. And as much as we might think that rational numbers is going to be an R, it's actually a Q with a line. Makes perfect sense, right? And some of this here is probably coming from the Greek or the Latin for the names, the roots of the names. So we're going to use more of those roots over the English roots. But our rational numbers. Questions on this so far? Now we're starting to really fill this number line out. We have the positives, we have the negatives, we have 0, we start getting some of the numbers between them. But actually, even with the rational numbers, we're not getting every number between, say, 1 and 2. Because we also have the irrational numbers. I've given here, these are just some examples of irrational numbers. Pi, we're used to pi, 3.1415926, and it keeps going on. It's a non-repeating, non-terminating decimal. Irrational numbers, we define them by any number that cannot be written as a fraction and has a non-terminating, non-repeating decimal number. That no matter how far out we go, it's not going to stop, it's not going to have a pattern. It's going to be considered irrational. Now the three I have up here, the first one is pi. We know pi from circles, geometry. We use pi a lot in geometry. For circles, finding areas of a circle, cylinder, a lot of rotational forces uses pi. Phi. I know the two of y'all have not even seen pi or probably even heard of pi. Phi, not pi, phi. I think you've heard of it, at least talked about some probably. It's the golden ratio, especially with Greek sculptures, the curl coming out. Might have covered it at some point, or at least talked about the golden ratio. If not, that's fine. It's not overly common, but it is considered the golden ratio of numbers. And the Greeks absolutely loved phi, this golden ratio, this arc, this curve. So they did a lot with phi. Again, it's another example of an irrational number. E we use with logarithms, logarithmic equations, log, natural logs. We're going to hit it in the spring. All of these are irrational numbers. And irrational numbers are our I with two lines. And it seems interesting that irrational numbers would get the I and not integers, but from my understanding at least, especially with just the history of math, we had, especially the Greeks and most cultures, had an understanding of irrational numbers. These here before we had a concept of negatives, these negative numbers in 0. Because for the most part, we didn't need negative numbers. Because IO, or even Mesopotamian or earlier, where we're talking about cattle, livestock, foods as sources, I'm not going to say I have negative 40 cattle. No, I owe 40 cattle to them. We don't think of it as negative. We just think of it, I need to give them 40. They need to give me 40. We think of it as just the number itself. Same thing with 0. There wasn't a necessity for 0. Romans definitely did not have 0. If you've ever worked with or seen how Roman numerals work, there is no base system with Roman numerals. There is no zero. Mesopotamia did have zero. If I know you all have not worked with different bases, I don't know if you've had like base 12, base 16. Mesopotamia, they had base 60. Base 12, base 16 is hard enough as it is, let alone base 60. It's interesting. But this concept of zero is very helpful. Now, the only other set of numbers that we have that we're going to look at are the real number system. The real numbers, which is all of this here. All of these are a part of the real number system. Now, interestingly enough, numbers can be a part of multiple sets. So a natural number, say 2. 2 is a natural number, which also means it is a whole number, which means it's also an integer, which means it's also a real number. 2 is not irrational. 2 definitely has a terminating 0, so it can't be irrational. But an irrational number is a real number. So they can be part of these different groups. But this also begs the question, if we have something that's defined as real numbers, that also means we must have what? Something that is not real or non-real numbers, yes? Well, we do. We call them the complex numbers or imaginary numbers. There is a group outside of the real number system that is called the complex numbers or imaginary numbers. We will talk about those when we start talking about quadratics and higher degree polynomial functions. And I will say at this point here, they do come in the form of a plus bi. I did miss this because the real number system is our R. Complex number system is our C. I do still think it's an interesting concept that we had irrational numbers, or a concept historically of irrational numbers. Phi e square root of 2 before 0. But questions on this so far? You ready for the next thing? So we're going to use brackets. We're not going to use this so much, the numbers, because we will whole numbers and all that reference them. But at this point, we're just going to write some sets. So we want to write the set of whole numbers less than 10. Excuse me. What's our smallest whole number? 0. 0. Yeah. Because natural numbers, yes. Natural numbers, the smallest one would indeed be 1. Whole numbers add 0, so we have 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Just 0 to 9. And especially with the whole numbers, this is nice. This is easy. We can list all of them out. We're good to go. How about the next one? Set of odd whole numbers less than 24. What would our first one be? 1. Then 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23. And that's it, because it's just odd whole numbers. So whole numbers is 0 and greater. 0 is even, so we have to start at 1. And then we're just going up by 2. And 23 is the last odd whole number. That is still less than 24. Now, both of these here, it's easy to use braces and just list the numbers out. We don't have to use the number types or specify anything else because it is easy to list the entire set. by writing it out. It does take a minute for the second one, but it's not something that we can't not do. We're good with these here. Next thing we're talking about is subsets. A subset is a set that is part of a larger set that's contained in the whole. So is when all members of one set or set A are also members of set B. When all members of one set are part of another, we call it a subset. So if we look at these two here, set A contains 1, 3, 15, 20, 27. Set B contains 1, 2, 3, 20, 11, 15, 27, and 100. Yes? Okay. Give you all a second to write. That's unfortunate. I feel like that's one of those things you can look back on and laugh, but it's not funny in the moment. So, as we look at this here, sets A and B, is everything in A, all the elements of A contained in B? Because A has what? 1, 3, 15, 27, 20, yes? Are all those in B? Yeah. So can we say A is a subset of B? Yeah. Now, again, I said it earlier. Some might disagree with me, but again, I say mathematicians are lazy. Because one way we can say this is set A is a subset of set B. Or, mathematically, we would say A subset B. A is a subset of B. Like I said, mathematicians, if we can write shorter, simpler, we're going to do so. A is a subset of B. Now, here's a question for you. Can we say that B is a subset of A? No, because everything in B, there's stuff in B that is not contained in A. So we have to change this statement a little bit. Draw a line through it. Now we've changed it to saying that B is not a subset of A. Is A a subset of A? So how do we define a set? A set, or a subset, a set is a subset if everything in it is also contained in the other set, yes? Is everything in A contained in set A? So can we say it's a subset of itself? Yeah, because everything in A is also contained in A, which means we can also say that B is a subset of B. It's a subset of itself. I think at some point you've had at least one teacher tell you that we do not write 0 with a line through it. Yes? That is not the same as 0. And the reason for this is it really comes in set builder notation, or sets. Because this here is the empty set. When we have those braces and a 0 inside of it with a line through it, we're saying this is the empty set, the set containing nothing. Now, it's very tempting to say, why can't we just put 0? Well, 0 is an element, it is a number. So the set containing 0 would contain the element 0. It is not empty. So here we have the empty set. And the question is, can it be a subset of A? Can the empty set be a subset of A? Let's think of it this way. So this classroom we're in here, yes? is a subset of the high school, yes? It's contained within the high school. If, let's just say this classroom, we empty it out completely, remove everything, would it still be a part of the high school? Because if we removed everything out, it would be considered the empty set. And the empty set can be part of the set. So we kind of get that, kind of wrap our head around that. We're going to get a little dangerous. You don't have to write this part down. Now the set containing the set containing the empty set, or the set containing the empty set, yep. Can it be a subset of A? Well, yeah. Because think about it, especially in terms of this room. Because if, again, we had this room completely emptied out, and we built a room inside of here that was also empty, would it still be a part of the high school? Yeah. So the set containing the empty set would still be a subset of A, yes? Are y'all starting to see where this is a treacherous road? Because we could also do the set containing the set that contains the empty set is also a subset of A, or worse yet, in some forms. Or the set containing the set of the empty set is a subset of the empty set. Nothing is a subset of nothing. That can get out of hand fast. And especially when you start talking about set and set builder notations and doing subsets, we specifically state in a lot of books, it's like, okay, list all the non-empty subsets. Because we don't want to mess with it. Because there's no way to list all that. That's infinite. We can keep doing that as much as we want. It's like adding zeros in front of a number. You can, there's not a lot of purpose in it, but you can. So, and even looking at this here, can we say that A is a subset of B? Yes, that's true. Is B a subset of A? No. So we kind of see how subsets work, yes? All right, let's actually list subsets. Writing subsets in set notation, write all the non-empty subsets, because we could be here all day trying to list all the empty sets. So if we look at the first one, 4, 5. What is one subset? The set containing what? Well, 4. Because if we just have the set containing 4, is that a subset of 4, 5? Oh yeah, that's one subset. What would another one be? The set containing 5. Or we could also have the set containing what? 4, 5. Because the set containing 4 is a subset of 4, 5. The set containing 5 is a subset of 4, 5. And the set containing 4, 5 is a subset of 4, 5. Not too bad. Now, we are not going to consider permutations. We're going to consider permutations the same thing. And what I mean by that is that the set 4, 5 is the same as the set 5, 4. That order does not matter. Now, for some things and some sets and some numbers that we talk about, order matters. Order makes a difference. And especially if you're talking about ordered pairs or numbers that are grouped together in a specific pattern, it's going to make a difference. Especially if you're using coordinate points to find locations, the point 4, 5 is not the same as 5, 4. Here, we're just looking at number groups. Those are going to be the same for us. Let's look at the next one, CD. What's one of our subsets? C. Then we could have the set containing D. And lastly, we could have the set containing CD. Yes. C, D, CD. Yep. We have two elements, two terms inside each set. We have three subsets. We feel good with these here. Are you ready for the next one? 2, 4, 6. Okay. Let's start with our subsets of one element. So we could have the set containing what? 2. Then the set containing 4. And then the set containing 6. Not too bad. But we could also have subsets that have two terms, yes? So what's the first one we could have? 2, 2, 4. We could also have what? 2, 2, 6. Have we done all the ones with 2? Because 2, 4, 2, 6. So what's our next option? 4, 6. Now we're not going to worry about 4, 2 because 4, 2 and 2, 4 for all intents and purposes are the same subset. Do we have any other subsets? Yes, 2, 4, 6. Excuse me. We feel pretty comfortable with this so far. It's a little interesting. We had 2 elements in it. We had 3 subsets. Now that we have 3 elements, we have 7. Let's see how many when we have 4 elements. What's our first set of subsets? Set containing E, set containing F, set containing, and the set containing H. Let's look at our 2s. We could have what? E, F. Then we could have E, G. Then we could have E, H. Well, that takes care of E, yes? Which one can we start with next? F, G. F, H. Okay, that takes care of F. And we move on to G and have G, H. We have now surpassed the previous one by a decent bit already, yes? And we haven't even finished because we can also not just have sets of 2, we could have sets of 3. Personally, especially when we start any of these here, I'm going to start from the left. So the first one, E, F, G, H. With the sets of 2, I picked E first, so E, F, E, G, E, H. And we moved on to F, G, F, H, G, H. I find it's easy to do this so that we get all of the iterations of it because we kept the first one the same and kept moving the second. This time we're going to keep the first 2 the same. So in that case it's E and F because we could have E, F, G, but we could also have what? E, F, H. E, F, G, E, F, H. Are there any others we can do with E, F? No, right? So what we would move is change it from E, F to E, G, H. And then we keep flipping that last one, the H. Well, the H is as far as we go. So we finished that one there. We would move the G if we could, but the G would become H. We're all out of letters with E, yes? So let's move E over 1. So since we're now not starting with E, we're now starting with F, yes? Which means we'd have what? F, G, H. Then we'd move the third one over as far as many as we can. Unfortunately, we can't move D over that. Those are all of our 3s. Do we have any other subsets left? We could also have itself. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15. We got all 15. It's kind of crazy how many subsets we get going that far. Would you agree? Now, throughout the year, I will say this every now and then throughout the lesson. I will say above and beyond. I know you've heard that when I say that time and time again. All that means is we're taking it a step beyond what we are, especially on homework, quizzes, tests. Just a step beyond, still just at least getting a way to wrap our head around this, especially subsets. You don't have to write this down. Number line. We call it R1. This isn't in the note sheet at all. R1, real number line, is the real number line. All the real numbers, yes? So mathematically, we call it R1. One dimension, R1. Now, for the most part, we can add another set of numbers to it. This here, we normally call this the y-axis. This is our x-axis, x and y-axis. We have the Cartesian plane, yes? We call this R2. Okay, didn't mean to erase that, but that's fine. So this is R1 of the Cartesian plane. We call it the real number R2 because it's a real number line or real numbers in 2 dimensions, yes? Now here's the question. Is R1 a subset of R2? On the Cartesian coordinate, the number line is contained in this 2-dimensional coordinate plane, yes? Because everything on the x-axis is contained in the xy coordinate plane. We can see that just fine, yes? Now, we do have an understanding that we also do have a z-axis, because we do live in a 3-dimensional world, x, y, z. We call this R3. And we can say the R2, the xy coordinate plane, is a subset of R3, the xyz. Yes? Which is also a set of R1. So R1 is a subset of R2, which is a subset of R3. We feel comfortable with this here, yes? We're about ready to step into a little bit of the uncomfortable. Because by this logic, we can say that R3 is a subset of R4. Of this 4th kind of dimension to it. Yes, mathematically we can say that's true. It holds up logically. Pictorially, do we have an idea of how that would look? Some do, some quantum mechanics, and some of those fields do have an idea of it. It's hard to write it graphically or conceive of it graphically, let alone saying R5. Because according to the mathematician or natural scientist, R4 we could consider time. Time is a 4th dimension. We can get there. 5, we're stretching it at least conceptually. But we could say this is a subset of Rn. Any kind of dimension is going to be a subset of it. Would y'all be like, I get R1, R2, R3, 4, I'm fuzzy. But essentially, we can keep going out, and it would be a subset of the higher order.